We're starting our new unit on graphing. We're going to look at different types of graphs and how to analyze them and create them. So the first thing we need to do is understand our graphs and how to read them. So the first thing is we tend to look for a trend in our graphs, meaning that it is a general direction for where our data set is tending towards. And this information can help us estimate the values in our graph. So if we're looking at a value inside our graph, that's called interpolate. So if a value falls inside, it's known as interpolate. We interpolate to find the estimated value. If the trend continues on the graph and falls outside of the range that's already given to us, then we have to extrapolate to find that value. So we have to go outside the graph to find the value. And then here are some terms that we need to know. The difference between discrete data and continuous data. So these are terms you need to know. First of all, discrete data, it is distinct values that can be counted. So for example, if I'm counting how much coin I have, I can count 1, 2, 3, 4, 5 coins. That is discrete data. For example, you could just also say the number of donuts in a dozen. That is discrete data. We can count how many donuts there are in a dozen. They're whole numbers. They're generally whole numbers. So that's discrete. Versus continuous, on our graph, there are data values that are connected. Or for example, it could be non-whole number sort of values. An example can be your weight. Because you ate too many donuts, maybe. And that's because your weight can fluctuate as well. From morning till afternoon after you had some water and food to nighttime. And your weight doesn't have to be, for example, 125 pounds. It could be 125.4. And then it could be 125.6. So your weight would be an example of continuous data. So it could be in the form of a decimal. Decimal numbers, certain fractions, and so on. Okay, let's look at our first example here. Okay, there's a nursery that grows and sells plants, trees, and flowers, and Lynn works as a grower there. For the winter holidays, Lynn is responsible for growing plants for a special display. 3 weeks before the busy holiday season, she tracks the growth on one of the plants. Okay, so we're given the graph already, and we're also given the data set on the side here, the table of values. So now we're going to analyze it. How tall is the plant on November 28th? So we're going to look at the bottom here, our x-axis to the bottom. This gives us our date. So November 28th, well, there's nothing on here that actually says November 28th. We can make a good approximation by looking in between the 26th and the 30th of November. So this would be November 28th, and if I look up, this is where I hit the graph, and if I look to my side here, it's about 50. So how tall is a plant on November 28th? It's about 50 centimeters. And did we interpolate or extrapolate for this? While we're looking inside the graph is a point in the graph, so this is interpolate. So how tall will the plant be on December 13? December 13, it's close to December 12, so maybe it would be about here. But if I look above it, there is nothing above for the graph. So what I have to do is I have to extend it and make an approximation now. So let's extend this graph by looking at its trend. Perhaps it's going to move semi like this, because that's the way it looks like it could be moving. And it's okay that we're approximating here because it's not given to us exactly. We're just approximating when we extrapolate. Okay, so now that I'm looking up from December 13, I hit about here, and that could be about 80. As long as you are fairly close to the value that it should be, that's okay for a quiz or a test or an assignment. Especially when you say about. Like I would accept 85. I would even accept 75 as long as you say about. And here, because we had to extend our graph, this is extrapolate. Okay, so moving on to the next page. So take the time now to try the try it yourself question. You might want to pause this video because I will give you the solution in 5, 4, 3, 2, 1. Okay, so Danny owns a small business that runs whale watching tours off a bay. And this graph shows the round trip distance of each tour and the length of time it takes to complete it. So how long would a 20 km tour take? So we're given the distance along our y-axis here. So that's where we're going to look for our 20. And that would be over here. This is our 20. And as I move along till I hit the graph, I look down and I see that I'm at 2 hours. Now saying how long would a 45-minute tour take? Well, in between the 40 and the 60 would be a 50. This would be a 50. So then if I'm looking for a 45, that should be in between here. Moving along, hit the graph, and I'm going to go down and look at my x-axis. Should be about 4.5 hours. So remember that when you're looking for points inside our graph, that's called interpolation. Okay, now a customer wants to charter Danny's boat for a 65K tour. Approximately how long will the tour take? So 65, well 70 would be right here. Oops. And then in between the 60 and the 70, be around there. And if I try to continue this, I won't hit anything. So that means I need to extend my graph. Just look at the trend. It looks like we have a straight diagonal across the boxes like that. If you look at the pattern. So now it has hit my extended graph, and looking at it, looks like it'd probably be about 6.5. So 65K tour will take about 6.5 hours. If a tour takes 8 hours to complete, approximately what distance did the boat travel? Okay, so now I want to start at the bottom here at 8 hours and move up until I hit my graph. Hits it right there, and that would be 80. So we would travel about 80 kilometers. Look at the pattern that we have here. 2 kilometers in 2 hours, 45 kilometers in 4.5 hours, 65 kilometers in 6.5 hours, and 80 kilometers in 8 hours. Can you see the pattern there? So you can see the relationship between the hours and the distance. So it seems like you're timesing it by 10. 2 times 10 is 20. 4.5 times 10 is 45. So it takes 10 times as long to reach the certain distance. Okay. Now we're going to look at describing trends in a graph. So Chelsea is a data analyst for Provincial Healthcare. She gathers the following information about the life expectancy of a 65-year-old male in Newfoundland and Labrador. This data will help doctors develop a healthy living campaign for seniors. What trends do you notice in this graph? Okay, well, let's take a look. So the remaining life expectancy in years in 2000 was, oh, there's a jump in this graph here. This means jump. But it's definitely a lot lower than in 2008 when the remaining life expectancy is 16.4. So what this means is remaining life expectancy at 65, they have about 15 years left, versus 2008, they have just over 16 years left. So, but what we do notice, though, that the life expectancy is increasing. Can this trend continue indefinitely, and why or why not? So can you imagine if we kept going on and on forever and never stopping? That would mean that this 65-year-old male would live forever. That his life expectancy will keep increasing, so this person will live up to not only 80, but then eventually 100, and then 150. Well, we don't have the technology now to figure this out, but as of now, that's not really possible. We don't have immortal humans, at least we don't think we do. So this would be a no, because if we continued indefinitely, it would mean humans would live forever. Or can eventually live forever. Maybe it can one day, you'll never know, but as of now, definitely not. Maybe not in our lifetime. We're going to leave the try it yourself for when I see you next. So you can work on Build Your Skills 1, which is on page 7 and page 8. So you need to get that finished before next class.